Hi, in this tutorial I'm gonna talk about the Harris corner detector. But before going to the algorithm, I'll do some introduction because we're gonna need them soon. So I will start by Taylor series. So if you remember, the Taylor series was to approximate the function around a certain point. So fx plus u, if you want to approximate the f around the x, so we have f of x plus f prime of x multiplied by u plus 1 over 2 second derivative of x u2 square plus some higher order terms. And if I just want to write it for a 2D function, it's gonna be something like this. Y plus v gonna be the value of x and y plus derivative of f respective to x by u plus derivative of f respective to y x and y would be plus what's a big one, 1 over 2 second derivative of x u2 plus derivative of first, so the relative to the y, the second time relative to the x uv plus f of y x and y v2 and some higher order terms, which we image processing usually care for the first approximation. First order approximation means we throw away whatever comes after this. So this is equation number 1, and as I said, we usually approximate with first order. Okay, so as I said, we usually don't care about this sentence. What we care is here. Okay, the other things that you need to remember is eigenvalues, eigenvectors, and PCA. So for a given data, let's say we have a data that has been distributed like this. So this is your data, and you can see it's 2D data, and it's been distributed actually in these directions. So the eigenvectors, which are always perpendicular, can if we apply the PCA on this data, it gives you the eigenvalue and the eigenvectors, and the eigenvectors are in the direction that data have the biggest standard deviation. So it will give you something like this. This is going to be first component, this is going to be the second component. So you can always use it to find the direction that your data actually being distributed. So this is for intuition. So if you have a matrix M, I mean your data, you could always write down your data in a form of a matrix. All these point here, which is size of d by d. The eigenvalue and the eigenvectors are, if you multiply by this eigenvector, it gives you the this. And we know that these are known zero value, because zero is always a obvious value. And if M is symmetric, means if M transpose is equal to M, you can always write M in the form of U1, which is a first eigenvector U2, UD, multiplied by lambda, which is corresponding to first eigenvalue, lambda 2 to lambda n, and multiplied by U1 transpose, U2 transpose, so U D transpose. So this is gonna be equation number 2. We're gonna need it soon. The other thing that is good to know is trace of a matrix. It's pretty simple. It's the numbers over this diagonal. So it's trace of A is equal sigma I over 1 to n A I A11 A22 plus A n. Okay, and the other thing is the definition of positive semi-definitive. Positive semi-definite. So if M is real and symmetric, and for all the value of if for all the number of RD, if Z transpose MZ is bigger than D, is it positive or bigger than 0? Okay, and this okay is equation number 3, sorry, and this equation number 4. Okay, so just remember these equations, we're gonna need them soon. Okay, now we can actually start talking about the Harris corner detector. So if you have an image which is something like this, and you have a perfect edge like this, these are dark area, there's a bright area, and the intensity is changing in one direction. So this is the intensity level, and you can see suddenly it goes down, so you can get the derivative, and you can easily find these edges. But edges are not very interesting. They don't keep very interesting feature from the image. It could be horizontal or vertical, but as I said, edges are not very. They don't keep very interesting features for our image. But some points like corners, they actually can tell us, can describe the most prominent or more interesting point of an image. So if we have a corner, an image, you can see the intensity is changing in both directions. So if I apply my patch, and move it, you can see I can get a very big response in this direction, in the direction of the corner. So what would happen if, well, if it's a corner like this, it's pretty easy to find it, but what if it's not? If it's like this. So if you remember what I just told you about the PCA can, the eigenvectors from the PCA can give you the direction that your data has the most standard, biggest standard deviation. So actually it can rotate it for you. So you can imagine that it is rotating you're rotating your axis, and see if on the new axis you have some big changes. So that's the intuition. This is a very loosely definition, but let us start writing the equation and see how can we find if we got a corner in our image. Okay, so we have a function and we're changing in the, we have to, it's a 2D function. You can change the direction and position of x and y, and we are applying a patch on our image at the point x and y, and this patch could have a shape, Gaussian shape, or a shape like this. This could be this or this, and this I returns the intensity at the point x and y, and actually we are interested to see if we shift or patch in the image, in which direction would give us the highest response. If it's a corner in both directions, give us a good response. If it's only in one direction, it means it's basically it's an edge. Okay, so here I will use the equation number 1, the Taylor series for this guy. And I approximate this part with Taylor series. So here I have an approximation. Then see denoted with this sign, which is an approximation. Okay, W, X, and Y, which is I told you just a patch, obviously 2D patch, and I have X and Y minus, and as I said, we use the first order approximation, so minus I have X, X and Y, delta X minus I of Y, X and Y delta Y power 2. Okay, so if these two terms will cancel out each other, and then I use power 2, and so I have X and Y power 2 delta X power 2 plus 2I X and Y I Y X and Y delta X delta Y plus I Y X and Y power 2 delta Y2. Okay, so I just write it down in the form of a matrix, which gonna be something like this. If delta X and Y equal delta X delta Y multiplied by M delta X delta Y. So M is a 2 by 2 here, and obviously these two need to be 1 by 2 and 2 by 1. So we can multiply, write in the matrix form and multiply them. So M is in this form. Okay, and as you can see, M is symmetric. So let's go to the next page. So if I use equation number 2, which was writing the matrix in the form of eigenvalues and eigenvectors, I can write it down as this. Where lambda are the eigenvalues and the R are matrix that I just built from concatenating eigenvectors. Have a look at the equation 2. I can just put it here again. This equation, writing the matrix with eigenvalues and eigenvectors. Okay, and we know that the eigenvalues are bigger than the 0, so I can actually write it down like this. Okay, and in this side I have RT, I have R, and here I had this delta X, delta Y, and here delta X, delta Y. So if I put everything together, I will have this. Okay, what I have now is delta X and delta Y are the orientation or the direction of changes. So if I just want to plot it, let's say this is my delta X, this is my delta Y, okay, and I apply RT on them, so this will rotate them. So I have another, now I have let's say, I don't know, it's here now. Now if I multiply it by this matrix, this part, lambda 1, lambda 2, well, you know, depending on the number and this matrix, it might, if they're all equal, it's just gonna stretch it, okay? But if they're not equal, if one of them is bigger than the other one, it's gonna skew it in one direction. So if they're equal and both of them are big, it's gonna stretch it. If they are small, if they are big. If they are small, lambda equal to lambda 2, and they are small, it's gonna shrink it. And if one of them is much bigger than the other one, it's gonna skew it on one direction, like this. Okay, so this is something that's very obvious from this matrix. Gonna share it or skewed. Okay. Now, if you have a look on this matrix, which I should have written down actually like this, or I could have just put a transpose there, just to make the multiplication possible, because it's 2 by 2 and it should be 2 by 1. Okay, if you have if you call this matrix A, you can see this guy is a transpose of A. Okay, this is here, the transpose, this is here, and this is symmetric and is here. And A multiplied by A transpose actually will give you the magnitude of a vector. So if you want to find the, you know that if you want to find the magnitude of the vector, you just do the inner product. Okay, so now, according to what we seen here, if my eigenvalues are small, so eigenvalues can tell us about the direction and the patch that we had. So if the eigenvalues are small, very small number, both of them, so we usually here, and we have a flat surface, flat region, means there's nothing interesting there. Maybe there are some slight changes, but not very much. If well, one of them is hugely bigger than the other one, if you remember from this, the change of direction gonna be like this, or if the lambda 1 is much bigger than the lambda 2, it's gonna be like this. So these are the delta x and delta y. So it means we were going to in this way, or we are the direction of change is in this way. That means it's a vertical edge or horizontal edge. So it means we have an edge. It's the same here. We're gonna have an edge like this. And if both of them are big, then that means we have big changes in one of these direction. So here we have a corner. If lambda 1 is roughly equal to lambda 2, and both of them are huge values. Okay, so we have to have a look on the eigenvalues, and based on them we can say if it's a corner or if it's an edge or if it's actually nothing. But the point is computing eigenvalues and eigenvectors are expensive. So in practical situation, we compute the R, which is determinant of M minus K multiplied by trace of M power 2. K, according to the paper from the Harris corner detector, is small values. It's some they computed empirically. It's somewhere between 0.4 and 0.06. So they said it's an empirical value. And trace of matrix from the equation 4, you remember, was sum of the element on the main diagonal of a matrix. So use actually R to distinguish if we have an edge or corner or nothing at all. So if R is minus value, then we have an edge like this. If R is minus value, again we have an edge like this. And if R is a positive value and is a relatively big number, that means we have a corner. So, and if R is a small number, that means it's a flat region. It's nothing interesting. Okay, so what you have to do, you have to actually compute the R, and as you can see, it's a relative number. You have to do some maximum suppression and see if it's big enough. Then you can tell if it's a corner or not. Okay, so I will put the code in the description, and you can see how you can practically compute the Harris corner from the scratch. One thing I think interesting also to add is to review the characteristics of Harris corner detector. So one of the first one is the rotation. Is it rotation invariant? Yes, rotation invariant. Yes. Why? Because we just discussed the PCA and the eigenvectors and the direction of changes, so it's rotation invariant. So if you have a chessboard, you can just turn it, and you're gonna see it a lot in the camera calibration that you use a chessboard. So actually you can use the Harris corner detector because it can find the corners even if they're rotated. Is it resistant to the illumination? The answer is yes and no. It's dependent on. So if my new intensity is alpha times xy plus b, if I just have a pure shift, if I only have this term, so it means I only increase everything by a fixed number. Yes, because in the Taylor series, if you remember, we use a derivative and they're gonna cancel out. But this guy gonna appear and it's gonna be multiple times, so it's gonna change. It's not gonna fix. And the other thing is scaling. So the rotation was okay. Changes in the illumination was yes and no, depended on the, we're talking about this term or this term. Scaling, no. Why? Because if you might have a corner like this, here you can see it's a corner. If I scale it, you can see it's an edge. So scaling, no. Okay, thanks for your attention, and have a good day.